So this video we will discuss one example, which is a turbine, and this turbine has gone through the isentropic process. So let's go ahead and start to draw our turbine. So this is our inlet, this is our outlet, and then we know for a turbine it generates the work out, right? So for this inlet, and they told us this is a steam, so it's water that enters this adiabatic. They said it's adiabatic process. Q is equal to 0, and initial pressure is 5 megapascal, and temperature is 450 degrees Celsius. And then the exit, the pressure has dropped to 1.4 megapascal, and then we need to find out the work out of the turbine per unit mass. So kilojoule per kilogram. And they also say this process is reversible process. Well, if it's a reversible process and adiabatic, the first thing we know from the last video, it's adiabatic. It's isentropic process. So we know it's isentropic process, which means S1 equal to S2. Then that will qualify this problem to be exactly isentropic process and for turbine. So how do we solve a problem like this? Now let's think about the governing equation for turbine. If you need to review the turbine concept and some examples we did, so you can look at the previous video in open system. Then work out how much work generated by the shaft when you have superheated vapor coming through the turbine, right? That workout is going to be equal to m dot. So you have workout transfer rate is equal to mass flow rate equal to times H1 minus H2. Okay, and also we know if this workout divided by mass flow rate, it's going to be equal to H1 minus H2, and the unit for this will be kilojoule per second over this mass flow rate is kilogram per second. So that's going to give us the unit of kilojoule per kilogram, right? Okay, and that's what you're solving. So in other words, this is H1 minus H2. That's our direction. If we find H1 and H2, we solve the problem. Now, knowing that, we need to find our H1 first. Since you know those two conditions for state 1, P1 is 5 megapascal and T1 is 450, we can look at our table. And for 5 megapascal, let's go to table A5. At 5 megapascal, which is 5,000 kilopascal, and our T is 263.94. So our T saturated temperature for at 5 megapascal, it's 263.94 degrees Celsius. However, our temperature is 450, which is way greater than this T sat. That tells us this is superheated. If it's superheated, we're going to go to correct table. And let's look at table A6. Table A6, we have pressure at 5 mega. Let's see, to 5 mega millitable. And temperature is 450, so 450 and 5 mega. And what we want to solve is H, right? So we go to H1. Our H1 value is 3317.2 kilojoule per kilogram. Now let's think about this problem. We also need to find H2. However, do we have two properties to find H2? We know one, we know pressure is 1.4, so we do need to find the second property. Where is that coming from? Yeah, right here. And that's critical piece we cannot ignore. Because it's isentropic, then we can find S2 equals S1. Then we need to go back to our table to find our S1. For the superheated table, I have 5 megapascal and 450. And what's our S value? 6.821 kilojoule per kilogram per Kelvin. Knowing that, we can go combining our second property, which is our pressure. It's dropped to 1.4 megapascal, that's given. Then we can go ahead find our H2. So let's take a look. We have to determine this state is what region. Do we have 1.4 megapascal? Let's see. Table A5. 1.4 megapascal, that's going to be 1400 kilopascal. And the second property is S. At S value, our S value 6.821, because at table A5 we learned Sg, saturated vapor, at this 1400 kilopascal. It is already 6.4675, right? And our value for S2 is 6.821. It is greater than its Sg value, which means this is a superheated vapor. If it is a superheated vapor, we're going to go to the table A6 and see if we can have 1.4 megapascal, and which is this table, and our S value is the 6.825. 6.825, it is between those two values, right? Okay. So we need to go ahead, list that. Looks like we needed to do a little linear interpolation in order to find that out. Let's list those two values, our S value and our H column. Our S value, we're looking at 6.7488. Corresponding H is 2927.9. And second, it's 69553 and 3040.9. And our S is right in between that, 6.821. That's our value. And our goal is to finding that H value. So we're going to use the linear interpolation to figure this out. So we're going to list our table, and we are using delta H over delta S. Delta H, we're going to use 3040.9 minus 2927.9. Delta S is 6.9553 minus 6.7488. That's going to be equal to 3040.9 minus our H2 value. Then corresponding S is 6.9553 minus our S value, because it's isentropic, right? So that's going to be equal to S1. Okay, then we can go ahead and solve this H2 value. And this H2 value give us about 2967.4 kilojoule per kilogram. And this value is indeed in between those two values. Okay? Then the very last step, so in going back to our original equation for this problem, we want to go ahead and find our H2 minus H1, because that's going to be our workout over mass flow rate, right? So that's our very last step. Okay, so going to do that, we will have our answer for this problem. And you apologize right here, my Surface Pen doesn't work right now, so but I think we're at the end. You can just plug your H1 and H2 into this step, then we get our answer as 349.8. That's going to be the turbine output per unit mass. All right, okay, I'll see you at the next one. Bye now.